as u to the 1/2. And then we see that we can use the power rule for antidifferentiation. So this becomes 1/3 times the antiderivative of u to the 1/2 as you go up a power to 3/2 and you divide by 3/2. So that's 2/3 times u to the 3/2 plus c. And so, oh, because I changed the problem. And so, what is this? This is 2/9 times 3x plus 1 to the 3/2 plus c. And if you're confident in the chain rule, you can almost just do this in your head and double check it. Let's see, 3/2 times 2/9 would be 1/3. 3x plus 1 to the 1/2, back inside 3, there it is. Okay, so that's definitely right. What's method number 2? It's just not even different, it's just the same thing, but it's just slightly stylistically different. Some people prefer this, and we should be aware of both methods. So it's the same problem. You still, I'll rewrite the problem, the square root of 3x plus 1 dx. And now you still let u be 3x plus 1. You still differentiate with respect to x and you get 3. You still do this, but now what some people prefer, I don't know, I find it weird, is to explicitly solve for dx. What is dx? Dx is just like 1/3 du. And I guess that's nice because it means you can just, instead of this undo the damage thing, you can just perform a direct substitution of 1/3 du for dx. But of course, you end up at the exact same place because what is this? This is root u. And now in place of dx, we put du over 3. But then that just becomes 1/3 root u du, and we're back exactly where we were over there. So either when it comes to being off by a constant, either just kind of stick it in and balance it out with some coefficients on the outside, or you can explicitly solve for dx in terms of du, and then pull your constants out, whichever one you like. Or you can do whichever one sometimes and some others. Okay, for real now, that was the lesson. Now I'm just going to do a lot of problems from this packet called Fun Times with Anti-Differentiation. And yeah, so I passed this out on the Friday of the last day of school, and if you didn't get it for some kind of reason, then you can download it, and the link is on Canvas. And we should do this entire packet like this week. And this packet is I don't want to say easy, but it's easier. It gets harder, so I think it's good that we're doing this first. And I will say also that in some years this was the so-called Wallops packet, the packet that I gave during Wallops to all the sophomores to work on. And so it's the kind of packet where you're meant to be able to just kind of get help from each other and tips and stuff like that, and just figure it out together. All right, I think I said that I would, now I sort of forget, but I think I said that I would do on the video pages 1, 3, and 5, and is that what I said? And then for homework will be 2, 4, 6, something like that. Some riveting video here. Oh man. Yeah. 1 through 5. Okay, so let's just go. Here we go. Fun Times packet. I'm just going to do all these problems and try not to talk too much. You can feel free to do this all by yourself, but at least check in with the video a little bit to make sure that you're following some strategies. And then we're going to do more of these next week that are harder. Okay, so let's go, and I'll share my sort of tips for understanding what to do and why, also kind of as we go. All right, so antiderivative of x over root 1 plus x squared dx. Does it look like some chain rule happened here? Yes, it does. because the derivative of 1 plus x squared is just, give or take, a constant x. And so that x reminds me of the back and side of the 1 plus x squared. And since 1 plus x squared is the inner function, then it makes sense that that's what's going on. Okay, so now I just do it, man. I just let u, I define this variable u to be 1 plus x squared. Du dx is 2x, just differentiating the right-hand side. So therefore du is 2x dx. And now I can rewrite my anti-differentiation problem in terms of just u's. So what do we get? Du is 2x dx, but I don't have a 2x dx, I have just an x dx. So I'm going to stick in a 2 and undo the damage with a 1/2. And now things are looking a lot better because this is 1/2. 2x dx is just du over, and this is just the square root of u. Okay, so after all that work, I have now determined that this is just 1/2 antiderivative of u to the negative 1/2. And now the problem has been greatly simplified because I can just focus all of my energy on anti-differentiating u to the negative 1/2 correctly. So that's going to be 1/2 times, well, what is the antiderivative of u to the negative 1/2? You go up a power to 1/2 and you divide by that power. So when you divide by 1/2 you get 2, so this is going to be 2u to the 1/2 plus c. And so this whole thing becomes just root u plus c, and then you always put your final answer back in the real variable, and so this becomes root 1 plus x squared plus c. And you can just confirm via the chain rule that that is the right answer if you ever doubt yourself. Alright, so what's really involved in these problems, I guess? Several things. At some point you do have to have like some just basic like skill, and you have to take some initiative, and you have to kind of be smart. It's not algorithmic. You do have to know what to set u to be. So here I took this sort of bold decision to define a variable u to be 1 plus x squared. Here it was kind of obvious, other times it will be less obvious. But after having done that, now it's just a matter of careful differentiating, careful substitution, constant balancing, anti-differentiating simple functions correctly. And by simple function I mean a function which for which there's a precise rule that, you know, for anti-differentiating power functions of this form. And then that's it. Okay, so once you get good at the algebra and the substitution and the chain rule, then really this entire skill amounts to recognizing what to set u to be. And there is no simple answer for how to do that that's going to work every single time. But after you just do a million problems, you just get better and better and better, and you just see the patterns. So I do think it's important to just do like a million of these. Okay, here we go. That's why I made a whole packet, and there's like a whole nother packet. Alright, here's another problem. How do we do it? Well, if you there appears to be some complicated mess here, but among the things going on is that x cubed plus 3x plus 5 is being raised to the 4th power, but in the denominator or something, so you might say to the negative 4th power. But whatever, there's some inner function. That inner function is a quadratic, and the derivative of that inner function is 2x plus 3. So, aha, I immediately recognize that this 2x plus 3 up here is just the back and side of the x squared plus 3x plus 5, which suggests that it's all going to work out. And so, I should let u be x squared plus 3x plus 5, and therefore du dx is 2x plus 3, and therefore du is just 2x plus 3 dx, and that is exactly what's up there in the numerator. And so I can just immediately rewrite this problem, because the constants all work now, as du over u to the 4th. And now I think it's very useful for beginners to put this in anti-differentiation friendly form. This is u to the negative fourth du. And what's the antiderivative of u to the negative fourth? You go up a power to negative 3, and you divide by negative 3. So this is negative 1/3 u to the negative 3 plus c. That is just right. And so, really, my answer is negative 1/3u cubed plus c. And really, my answer is negative 1/3 times, because u, after all, was really just x squared plus 3x plus 5 cubed plus c. Ciao. Okay. And there's not a lot of space on this board, but there's not a lot of space on your paper either. So I'm sorry about that. This packet was sort of made many years ago. I think I would space it out more now. Okay, now I'm going to try to talk a lot less, and I'm just going to do a lot of problems. So let's go. Keep watching, or you can turn this off and just do them all yourself. Tan theta secant squared theta. Okay, well, I immediately recognize, well, no, this time perhaps it's harder for you to recognize now that what's going on. But I recognize immediately that secant squared is the derivative of tan. So if secant squared is the derivative of tan, then does it look like some chain rule happened here? Yes. I should set u to be tan theta, and then du d theta is, well, the derivative of tan theta we just said is secant squared theta. And so du is secant squared theta d theta, and so this just problem becomes immediately u du. What's the antiderivative of u du? U squared over 2. Ta-da! Therefore, this problem becomes 1/2 tan squared theta plus c. Shot. Oh yeah, more. 4. This maybe is kind of hard. I don't know. So dt over root t times 1 plus root t cubed. Okay, what's going on now? Well, perhaps now it's a little less, it's obvious to some people, but less obvious to others that there's an inner function and an outer function. The inner function appears to be, it's going to be very loud. The inner function appears to be 1 plus root t, and the outer function appears to be like to the third power, or to the negative third power. And if you differentiate, so what makes this hard is you need to be so good at differentiation and you need to do some algebra in your head, because you need to try lots of different things, and among those things that we should try is to differentiate 1 plus root t. And what is the derivative of 1 plus root t? Well, it's going to be 1 over 2 root t. But that's what that is, because this root t is down here in the denominator. So I guess maybe here it's less obvious, but it's obvious to me because I'm experienced, that this 1 over root t thing that's just sitting here is in fact the back inside of this 1 plus root t. Okay, let me just do it. So I let u be 1 plus root t, and so what's du dt? Well, okay, doing some things in my head, I just know, because I've been doing this a million times, that the derivative of t to the 1/2 is 1/2 t to the negative 1/2. In other words, 1 over 2 root t. And therefore du is dt over 2 root t. And if du is dt over 2 root t, then now I hope you see that, oh, that's almost exactly what we have here. What's missing is just the 2 in the denominator. So I put 2 in the denominator and a 2 in the numerator. on the outside to balance that out. And then, then this whole sort of thing here inside that green circle is just du. And so this problem reduces to 2 times the antiderivative of du over u cubed. Wow. And so this is really 2 times the antiderivative of u to the negative 3 du. I do this all out every time. And what's the antiderivative of u to the negative 3? Well, again, you go up a power, but that means to negative 2. And then you divide by negative 2. So that's going to be, so it's like negative 1/2 times u to the negative 2 plus e. Cha. And so then this answer is, in fact, just negative u to the negative 2, or negative 1 over u squared. And so the final answer to this problem is negative 1 over 1 plus root t squared plus c. Okay, good. Halfway done with page 1 of 6. Wow. Just gonna keep going. Although I might take a break at some point. I think this explanation was good, but like many of these videos, perhaps, hopefully you're watching on 1.5 times speed at least. Oh my god. Okay, continuing on, and they do get kind of easier. And if you find yourself, well, okay. Here we go. X to the 4th times sine of x to the 5th. Okay, well, come on. This one just is easy, because this x to the 4th is just clearly the back and side of the x to the 5th, because the derivative of x to the 5th is 5x to the 4th. And so just almost without even thinking, I just know to set u to be the inner function. And the goal here is for you to do so many of these that it just becomes automatic. That this is 5x to the 4th. And so du is 5x to the 4th dx. And thus what's missing is this 5. So I put in the 5 and I undo the damage with the 1/5. That is great, because then I get 1/5 times, well, that's, well, 5x to the 4th dx is just my du. So this becomes sine u du. What's the derivative of sine u? Negative cosine. Because the derivative of negative cosine is sine plus e. And so this is negative 1/5 cosine of x to the 5th. Alright, you might be tempted to do this problem in your head. Please don't. Even if you think you could, your error rate starts to creep up when you try to like just do this all in like one step. This to me is like the appropriate amount of work to be shown, and I think this is good. I think I'm modeling good behavior here. Okay, more. Here we get one that's a little bit more interesting. X over 1 plus x cubed. Okay, this is more interesting because I have something to actually say now. Well, if you just, well, here it's just not clear that what's going on, because the derivative of x plus 1 is 1. And so I don't know what this x is doing here. Okay, so this is an example where you really do, this is really more of a kind of a craft. You have to explore and play and try things and sort of fail a little bit and try new things. I know what to do here, and that's because I'm very experienced with these problems. And In particular, there is a kind of a principle at play, which is that because the derivative of the sum of two functions is the sum of the derivatives, what that means is that we can if you want to differentiate a whole big thing, we can differentiate them piece by piece. Similarly, we can anti-differentiate things piece by piece and put them all back together. Therefore, at any opportunity, if you can anti-differentiate if you can split the thing you're trying to anti-differentiate up into small pieces, then that's good. Here, it's not clear how I can do this. Basically, when I have fractions, I want, if at all possible, my denominator to be one thing. And that's because, as everyone learned in 7th grade or something, or perhaps pre-calc A, that if you have some fraction and you have sort of two terms in the numerator, one term in the denominator, this is very easy to deal with, and so that's like great. But when you have two terms in the denominator, then there's just really nothing that can be done here. So if you have a mixture of complicated and simple things, you would prefer your simple thing to be in the denominator, because that facilitates being able to split the fraction up into pieces, and then maybe it will become easier. Okay, so keeping that in mind, then I'm going to just, even though it doesn't obviously help me, I'm going to let u be x plus 1. Okay, this is great, because if I now differentiate, I get that du dx is, well, the derivative of x plus 1 is in fact just 1. And so du just is dx in this case. Okay, how is that helpful? Well, if I go to rewrite this thing, my denominator is now u cubed. What is my numerator? Well, what is x? X is just u minus 1. Ta-da. And since x is u minus 1, I can rewrite this as u minus 1, and then dx is just du. Have I accomplished anything? It seems I've just sort of shuffled things around in a different order. Yeah, that's true, but now I've shuffled them around in an order in which my denominator is a single term, and that means that I can split this up into the antiderivative of 1 over u squared minus 1 over u cubed. And that's just good, because this is just u to the negative 2 minus u to the negative 3. And these things aren't easily differentiable. I mean, I'm really splitting this up into two antiderivatives, but I'm not bothering to write it. What is the antiderivative of u to the negative 2? You go up a power to negative 1, and then you divide by negative 1. So that's negative 1 over u. And what's the antiderivative of negative u to the negative 3? You go up a power to negative 2, and you divide by negative 2. So that becomes plus 1/2, or 1 over 2u squared, I guess. And I'm just double checking that, but yeah, it's totally right. Plus c. And therefore my final answer is negative 1 over x plus 1 plus 1 over 2 times x plus 1 squared plus c. Whew, that was pretty fun. More. Number 7. Antiderivative e to the sine x cosine x. Okay. Well, once again, to me this is clear that the outer function is e, the inner function is sine, the derivative of sine is cosine, so this problem just does itself. Let u be the inner function, differentiate both sides, this is cosine, so du is cosine x dx. That's exactly what I have here. Thus I can immediately rewrite this problem in terms of u. This is e to the u du. And the antiderivative of e to the u is just e to the u. We'll see. Because, yeah. So, this becomes e to the sine x plus e. And that's it. All right. 8. Yeah. So 8. All right. I need to anti-differentiate sine theta over cosine squared. Okay. Well, just immediately, because I'm a beginner. Well, because you're a beginner, I guess. I will rewrite this as cosine theta squared, because that's what that really means. And now you have to put on, you have to be the detective, and you have to say, does it look like some chain rule happens here? And the answer is, yeah, it does look like some chain rule happens here, because there's kind of an inner function cosine and an outer function squared. And this sine up here, you need to train yourself to recognize as the back and side that comes from differentiating cosine. In particular, the derivative of cosine is negative sine. So give or take a constant, that really is just the derivative of that. That suggests that we should let u be cosine. Then du d theta is negative sine. And so du is negative sine theta d theta. Having done that, I now see that the numerator is almost exactly what I need it to be, but I'm missing a negative. So I stick in a negative, I undo the damage with a negative on the outside, and then I get negative sine theta d theta is just du, and down here is u squared. Okay. What's that? It's negative u to the negative 2 du, and the antiderivative of u to the negative 2 is up a power to negative 1 divided by negative 1, so it's negative 1 over u. And so this final problem is just 1 over u plus c, and so it's just going to be 1 over cosine, or I guess you could even just say secant. Did I write that? Yeah. So the final answer here is just secant theta plus c. Okay. And, oh, by the way, this is the long way to do the problem. The smoother way to do this problem, which perhaps I should have noticed, but I was kind of on autopilot. Take this original problem and just rewrite it as sine theta over cosine theta times 1 over cosine theta. But then that's just tan theta, and then that's just secant. Haha! Do you know how to differentiate tan theta secant theta? Well, you should, because that's just a rule. In fact, we learned a long time ago that the derivative of secant is secant theta tan theta. So perhaps now, just by memorized rule, you can now say this is secant theta plus c. But if you didn't see that, you could just go through what we've done here. All right, that was page 1. I know I promised to do pages 1, 3, and 5, so I guess I'll follow through on that promise. But feel free to turn the video off at any time and just do these all yourself. We're going to do this entire packet. It's great. You can just do it while watching TV. It uses up a very specific and small part of your brain. But it is important, I think, to do a lot of these problems and to get really good at them via practice. So, okay, I'm going to pause this video now and return in a minute to do pages 3 and 5. And you can just watch all the way to the end and follow along with me, or turn this off, and then you're going to do pages 2, 4, and 6 by yourself. Okay, bye.